last couple of lectures were on flow equations in real space. So, we were discussing velocity field, equation for the velocity field, energy in real space. Now, we are going to go to Fourier space. Okay. Now, I will motivate by some logic or some ideas now, and also over time will become clear, why Fourier space is very important for description of multi-scale problems which has many scales. In fact, I have been giving example, turbulence being one of them. So, why is Fourier space important in turbulence? So, you can see that these are vorticity magnitudes. So, curl of omega squared, okay, and these are structures which are of different sizes. Okay. Now, like you have bigger structure here, the small structures, and in fact, it is somewhat similar to what we have in the sky. The structures in the universe, we have very big structures, super galaxies, then we have stars, then planets, and within planet there are different scales. So, if you use in fact linear scale, that is not a good idea, or in fact you can't, if you describe in terms of linear series, it becomes quite problematic to represent them. Okay. So, Fourier tells you that you can describe at different scales. So, first Fourier mode corresponds to large scale, then you go down to second Fourier mode with half the scale, third Fourier mode is 1/3. So, this is very convenient. Okay. Now, we will see its importance over time. You really realize that without this we can't really describe many aspects of turbulence. So, turbulence is a multi-scale problem. Fourier space captures this multi-scale physics very well. Okay. So, I will keep emphasizing it over time. So, we can study the large scale, or this k means wave number. Okay. This is small wave number. So, small wave number corresponds to large scale. K is 1 by L, everybody knows from this stuff. Then computation of energy transfers. So, as I said, when you supply energy in a bucket of water at large scale by stirring it, then it goes to small scale, and there energy at every scale. In fact, similar to this problem, there are energy at different scales, right, omega squared. Now, energy flows from one scale to other scale, and the example which I kind of like is this money flow. From example I gave, that we have central government which has budget allocated for the whole nation, then it goes to state level, district level, village level, and this is not in real space, these are collective phenomena. Okay. So, you can't really think of as real space. So, this is scale by scale transfer, or in fact we can think of these fractals. No, this is example which is given. So, there are fractals, and within this area there is fractals. So, here it is important to use Fourier kind of representation. Different scale has different physics, and we will use Fourier transforms to especially study this energy transfers. That is what we will do. Okay. So, I will again divide this Fourier description in 5 parts. So, definitions, we will review definitions. You know it, but I am just going to do it define for this course. There are variations in definitions. So, I will stick to my definition for this course. Okay. And please stick to the signs. So, I am going to emphasize some science is important. So, what sign convention I use? A flow equation in Fourier space, then we will do. Then kinetic energy is very similar to what we did in real space, but I am just going to do all of what was done in real space in Fourier space, and then we will do vorticity, kinetic helicity and entropy. Then I will illustrate in fact the same examples which I did in real space, and you see some benefits right away. Okay. So, but not all of it, all of it will take time. So, we first start with definitions. So, Fourier. So, in fact, I just want to say that the first time Fourier gave his theory was in 1807. So, it is 200 years back, and he solved heat equation using Fourier transforms. So, this is done in math methods or your mathematical physics course, and This paper you may know that it was rejected, in the sense the big shots at that time did not really accept their idea. So, the big shots were Lagrange, Laplace. So, this is French school, so this is French people, and they said, oh, so Fourier series does not well, convergence of Fourier series is very difficult to prove. The proof was given many years later. So, it is like engineering kind of, so he gave a series and he said, well, we can use that series to solve this problem, but the proof was given much later. So, he wrote a book, and in that book he put all that idea. So, a Fourier series, the idea is that we have a box. So, this is a 3D box. We can also do for 1D and 2D, but we will I will illustrate for 3D, but if you can do for 3D, you can always do for 2D, right, or 1D. So, this box has to be periodic. We can also generalize it to box with non-periodic boundary conditions or vanishing boundary condition, but periodic is easiest to illustrate. So, I will stick for this 5 modules to the assumption that box is periodic. So, periodic means this wall at any position has the same. So, if I go across by distance Lx, other corner, I should have the same value of the function, and this periodicity can be for any function. So, here I am going to use velocity field, pressure field, energy, but it will be same if I go across, or along y direction. If I have something here, then it will be that, or inside also. If I have some, let us say some point, some side inside, then is periodic means I have to make another box which will behind, and I cover again distance Ly, then you find that it has the same value. So, this is not one box, it is like periodic means there are infinite boxes, something similar to which I was showing about this cyclones and anticyclones. So, there are cyclone and anticyclones in the neighborhood, then there is a anticyclone has cyclones in the neighborhood. So, it is infinite lattice. Okay, so, we assume this is periodic, then the definition is here. So, u r t. So, this is vector field I gave for vector field, but you can also write scalar field straightforward. So, basically there are 3 components. Okay, for every component I can write like that. So, this is a real space, R is a real field. This is in fact my general notation. Okay, R means real, T is time. So, I just keep time in it. So, our function is function of time. This is a wave number. And I k dot r. So, you take a dot product of k and r. So, you can take then origin, origin is here. So, this is a vector r, but this is a corresponding space. Now, Fourier space is not this real space description, this one. Now, I can also have a Fourier space description. So, its axis will be kx, ky, kz, and this is a different space. Okay. So, 0 0 0 0, this is 0 1 0, no, ky is 1. So, this is 1 0 0. So, we have a grid. For now, this is a box. What I am considering right now is a box. So, my k vector, in fact I have it in the next line. My k is discrete. So, kx, this is by Fourier. Okay, this. So, the kx. So, this is lattice. This is a lattice. I have this points. In fact, it's equi-space points in this Fourier space, and so I can draw a vector k. So, it has kx component, ky component, and kz component, and they are given by these numbers. Okay. Now, you can see that exponential I k let us put along x direction. So, I do not want to write all this 2 pi by Lx times x. This is the first one, no, 2 L pi by Lx into x. Now, similarly, write for y 2 m pi Ly. Okay. Now, this function is periodic with x along x direction with period Lx. Yes, yes or no, this function. So, you can just put e to the power I 2 pi L by Lx. If you put x plus Lx, so Lx will give you 1. So, the new thing which is coming is e to the power I 2 pi L x plus e to, so this will be e to the power I 2 pi L. So, e to the power I 2 pi L is L is integer, L is, so I will show that L, M, N are integers. They can take both values negative and positive. For Fourier periodic box, it is both takes both positive and negative values. Okay. So, this function is periodic. Similarly, the y part will also be periodic with Ly period and same with Lz. Okay. So, these basis functions are periodic, and that is why we need to use a periodic box. Okay. So, we can get, you can represent any, so this statement of Fourier is that any periodic function, so this has to be periodic function. Any periodic function can be represented as a series, and what are the amplitude in Fourier space? These are the amplitude in Fourier space. So, this is called Fourier mode. This is, I am going to call this as Fourier mode. So, this is what Fourier assumed for 2D plate. He solved for 2D plate heat equation, but we will solve for 3D flows or 2D flows also. Now, I think I missed, yeah. So, I am going to erase some of this stuff. Now, I can invert. So, given UK, given Fourier modes, I can get U of R, right. This is called from transform from k to U of k to U of R, but I can also go backward. I can do from, so I can compute UK given UR. So, this is very easy. This I will leave it for you to do it. You just integrate this object and multiply by e to the power minus I k dot r. Actually, you should use k prime, not k. Okay. So, this is straightforward derivation from here to here, except you have to use one identity. There is an important identity which you need to use. So, I am going to write in this corner exponential I k minus k prime dot r integral over dr. Now, what is this object? So, I have to do over full box. So, the integral over the whole box. So, this one, since it is periodic, so k minus k prime, if it is a integer, right, rather sorry, it's a number, not integer, sorry, L, M, N are integers, so k minus k prime is a number. So, if this is a number, then what is going to happen to this, to the thing? So, this is going to be periodic, no. So, periodic function, if I sum over the volume, it should give you 0. So, one simple way to, when you can do it for all three, but a periodic function sin x over whole period is 0 integral. Okay. So, this is a periodic function, this is 0 unless this exponential becomes 1, and when does exponential become 1? When k equal to k prime. So, this is delta k vector, these are vector, okay, k prime equal, and if it is equal, then what is the value of the integral? So, this becomes 1, so is dr, which is volume. So, I should put Lx, Ly, Lz. So, this is my value of the integral. So, this is the definition. I mean, I will not, there are books written on it, you know, the mathematicians still work on this integral, which functions are different, Fourier transformable, which are not, but we will not go into that. We just need to know the definition both ways. No, so sawtooth function I am not, so this function, periodic function. So, this one can be written as, so this one is, so just, okay, let us make it exponential of I k double prime dot r. Okay. Now, this has cos k prime dot r plus I sin k prime dot r. So, this is 0, no. So, I am only claiming that this integral is 0 unless k equal to k prime. Okay. So, let us go to the next slide. So, this is a nice thing I saw in Wikipedia. The picture is not coming out nicely, but I kind of liked it. So, today I just put in the slide. So, this is a circle and there is a rod, which is going around the circle with constant velocity, angular velocity. So, the y component, so there is a rod which is moving only horizontally. Okay. So, basically it picks up the y component, this y component. And if you plot the y component, it looks a nice sine curve, which is of course straightforward, because it is r sin theta. Okay. So, it picks the first r sin theta. Now, I want to get sin theta plus sin 3 theta. What do I do? Well, this one, this normalized properly, this one. So, you make another circle of radius 1/3. Now, this both of these guys we are going to go around. Okay. So, now here, so this is loop within loop, this is called EP circles. So, EP cycles. So, this first guy is going with constant velocity and other guy is also going around like that, and there of course there has to be a relation between the two, and then this is sin theta, this curve is sin theta plus sin 3 theta, and I can construct similarly. So, these are 3 EP cycles. I am not sure you can see this properly. So, 3 EP cycles, and you can make 4 EP cycles. So, this is a nice illustration that you can construct Fourier series by EP cycles. Okay. Anyway, you look at Wikipedia Fourier series and you will find this example. It's in fact, it is animation. So, this for the side. Okay. In fact, according to the Fourier series, any periodic function can be represented as a Fourier series, any periodic function. So, keep this in mind. So, this illustration I am giving you only for 4 basis functions. Okay. Now, velocity field is real. So, that means we are not really working with complex functions. So, there is some condition which is there for Fourier modes. UK means Fourier mode for me. Okay. So, what is the condition for UK? So, this is my by definition. So, actually I should go back. Please remember here this is plus sign here. Okay. This plus sign is my notation. Well, notation used by 1/2 of Fourier people who use Fourier. So, U of r is e to UK e to plus I k dot r, but if you go to the inverse space, then it becomes minus. This is U of k is U of r exponential minus I k dot r. Okay. So, this notation is followed by some, so not by others. Some people use this as minus, this one is minus, and this is plus. This is plus. Okay. So, but I will use this notation throughout, and you should also use that, because I will get confused otherwise when we talk. Okay. So, what about U of minus k? So, since there was a plus sign here, but I am using minus k, so this becomes minus k, right, by definition. U of minus kt will be, oh, it should be plus, it should be plus, it should be plus, it should be plus, because there is a minus there, is a plus. Now, what is U of kt? So, this 1 over volume Lx, Ly, Lz integral dr U of RT exponential minus I k dot r. That is what I wrote in my definition. They are vectors. Huh? If I take a complex conjugate of this, what I just wrote, so what will I get? The right hand side will be, so U of r is real. So, complex conjugate does nothing to U of r, it only will act on the exponential. So, that will give you exactly this, right. So, what does it mean? U of minus kt, this one is same as complex conjugate of this object, which is here U of star of kt. So, U of minus kt is complex conjugate of U of kt. Okay. So, these are real complex numbers. Okay. U of r is real, but U kt is complex. So, this is very important and we need this all the time. Now, advantage of this relation is that we do not need to save all the modes in computer, we need only to save only half of the modes. Now, I will illustrate this using a figure here. So, this is my, in fact this is in Fourier space, so you should really call it kx and kz, but in my notes I may not write k, When I write x in Fourier, that means kx. Now, if I am given this one, this Fourier mode, its value is alpha. Alpha is a complex number. What about Fourier mode for wave number minus k? So, minus k is in the opposite direction. So, this Fourier mode is alpha star. So, there is star sitting here. I have a vector k here, which is beta. Then what about minus k? Is beta star. So, this must be satisfied, otherwise there is a problem in your calculation. U of r will not be real if you do not satisfy this. Okay. So, we need to use this quite often in our derivations and so on. Okay. So, some properties. So, Fourier series has some very interesting properties, and one property is that, so if I have real, these are real space products. Okay. So, this really means f of r, g of r. Now, this means this is a function, f g is a function, real space function. Take the Fourier transform of that. So, Fourier mode for f g is this. So, I am summing over p, this summing over p, and then you have g of p and k minus p. That means p disappears, and this right hand side is only function of k. Is that clear? So, this is called convolution. So, I have to convolute, means, so this implies, so like if I were to write g of 1 and k is some k, okay, in 1D, let us just do 1D, f k minus 1 plus g of 2 f k minus 2, like that. Is that clear? So, k is fixed, but you have to sum over all p's. So, this is a sum. So, right hand side is the left hand side is only product, but if I do the Fourier transform of a product, in the Fourier space I will have sum. So, this is could be expensive. So, I can just multiply a number by one shot, but if I want Fourier transform of that thing, then you have to, in Fourier space I need to do this convolution. So, how do I prove it? So, I will prove 3 theorems, okay, and just to show you how to work with Fourier. So, f g, no, so f g, so this is f and g. So, by definition, what is the Fourier transform of f g? This is by definition. So, this is really a function e to the power minus I k dot r. Okay, these are definition. So, f g should really treat as a single function. Now, I am going to write f of r and g of r as Fourier transforms, as Fourier series. So, this is f of r written as f q exponential I q dot r. So, I club together. So, this q dot r is part of this f q. Then g of p. So, g of r written as, and there is sum. Okay. So, there is sum here. G of r g p exponential I p dot r. Then sum over p. Is that okay? And e to the I minus k dot r is here. So, I just try to combine, I mean, otherwise this will fill up the whole page. So, f of r and g of r has been expanded as Fourier series. So, this is called expand, you write as a series. Okay, what next? So, what is this object? This, now this dr integral, so I am swapping, no, this dr integral is coming in and the sum is going out, and the sum is over all p's and all q's. So, sum can be swapped. So, what is this object? This object is a delta function. So, this is 0 unless p plus q is equal to k. This argument must become 0 unless it is the integral will be 0. So, this is what I wrote here, and if it is 0, then my volume will come into factor. So, Lx L by Lz, and this object will get cancelled with that. So, we have f of q, g of p, delta p plus q minus k, and 2 sums. So, now with delta function I can replace one sum. Now, everybody is kind of comfortable with delta function. Okay. So, I can replace q. So, this q, so because of this condition, what is q? Q is k minus p, right. So, this must be 0, p plus q minus k is 0. So, q is equal to k minus p. and that is what we have at the top. So, I replace one sum and that becomes k minus p g of p. So, this is a proof, and so if you have product in real space, in Fourier space that will be sum, and this is called convolution. Okay. I will not prove it right now, but you can also have things like product f k g of k in Fourier space. Now, what happens is this? What happens to this in the real space? So, if I do the transform of this to real space, so this also will involve convolution, but I will leave that is for you to as a exercise for you. Okay. So, I will not do this here. Okay. So, this I will need it all the time. So, product, in fact, you have u dot grad u, right. So, it is a product of two functions u and derivative of u, and we will need Fourier transform of that product. So, I am going to use this relation. Okay, property 2. So, derivative of a function. So, I know f of k, but which is Fourier transform of f of r. So, I may say, well, let us take the derivative of f in real space. So, gradient involves derivatives. So, I am looking for I have this function, I have this derivative df by dxj. So, this is shorthand notation, xj could be x or y or z. So, x1 is x, x2 is y, x3 is z. So, what is the Fourier transform of this object? It is ikj fk. Some people use a hat, they use a hat here, but I am not using hat. So, just too many hats to write. So, I started following without hats. Okay, so let us start it. So, I am interested in this derivative. So, again I just start with the definition. So, this is a function. So, I just put this function here and this is a definition. Now, use integration by parts. So, this is one function, other function. So, I would like to integrate the first one. So, we write the next one. So, first function integral of second. Okay, this first function integral of second. So, that will give you. So, integral of second will give f of r, right, it is a derivative, so integrated, and this first function. Then derivative of the first function, which will be, there is a minus sign. So, in the definition the minus becomes plus, there is a minus coming from here. So, minus becomes plus. So, derivative will give ikj, the derivative with related to xj. So, that gives you ikj. So, it could be kx when I take x derivative or ky when I take y derivative, and kj is not a function of r. So, it comes out of the integral. So, kj is outside, and the second integral of the second function, which is f of r, this one. Okay. So, derivative of the first function is ikj e to I minus k dot r, with a minus sign, minus becomes plus, and this is integral. So, what do I get? So, for periodic function, what is the surface term? 0. So, first term is 0. So, I have the, and what is this object? Divide by this. Okay. So, this integral divided by Lx, Ly, Lz is what? Is a Fourier transform of f of k, f of r, which is f of k. So, that is what we got, that is what we want. So, it is ikj f of k. Okay. So, straightforward, but we need this all the time. So, you just have to remember product becomes convolution and the derivative becomes ikj of that function. Property 3. So, this average means, I am not doing average. For me it is a volume average, means I sum over, I integrate this function integral f r g r dr divide by volume Lx, Ly, Lz. So, it is not like averaging over random variables. So, I am not doing those operations. I just say volume average means I just integrate over the volume and divide by the volume. Okay, you can call it average if you, yeah. So, this is my bracket, okay, it is like a special volume average. Now, this is equal to f star of p g of p, real part of this means real. Remember, f and g can be complex. So, the star here, now you see there is a complex conjugate has come. So, I do not multiply by Fourier GP, Fourier FP, but I had to, one of them must be complex conjugated, and it does not quite matter, you can complex conjugate second one, because this sum is over all p's. You can, whether you can show it yourself, I am not going to show every little step, but this is same as sum over p f of p g star of p, is exactly same when f r and g r are real. Okay, so, that is our assumption, my f and g are real, okay, and f r and g r are real, but f k and g k are not real. So, how do I prove it? So, I need this for energy, So, in fact, when f and u both are u and u and take a dot product, then that is energy. So, right side also we should have relation. Huh? P is Fourier mode. So, right hand side is Fourier, left hand side is real space.
So, why are you using P instead of K?
I could use K, yeah, I could. So, in my derivation, in my notes it was P. I could use K here, no problem. It is a dummy index. Okay, the proof is also very easy. So, this is by definition, I just wrote that. So, now write f of r and g of r as Fourier series, right, this is straightforward. In fact, it is simpler than proof 1. Now, this one is delta function. So, this cancels and we got the proof. So, p plus q is 0. So, q must be minus p. So, that is what we get. So, f star of p. Now, I can sum this over with minus p as well. This is p is a dummy index. So, instead of summing from left to right, I could go from right to left. Minus p means right to left, no? So, these two sums are exactly equal and put a factor half. So, this was what I got. So, f of minus p is what? This is f star of p, okay. This is reality condition. So, now I just sum up of that. Now, I can just, instead of now minus p, I can make it plus p, is a dummy index. So, I can always do this. So, what is this plus? So, we need to, so this is 1 and I want complex conjugate of this. So, this is complex conjugate. So, this will give you, just do the step, this is same as if I just do over some p. So, this is f star of p g of p, okay. So, this is bit of step. So, just put a complex conjugate. So, function plus this complex conjugate is real. So, this is what we get real. So, it is real part of f star p g of p. It must be real function, right, because this is real. So, this will give you that. Okay. So, we need this for energy, helicity, but please remember this, one of them must be star. You simply do not multiply by FPGP, one of them must be complex conjugate, and either one, because I am summing over all p's. So, there is minus p as well as plus p. So, as a result, for energy, so energy is dot product of u and u. So, of course, that means you have ux square, uy square, uz square. So, this will be u star k dot u of k. So, there are 3 terms. Now, what is u star k dot u k? Is a modulus, is a complex mod squared. So, this is just mod square. So, I have all the Fourier modes, I need to take a absolute square and sum over all k's to get the average. Now, this is when both the fields are same, but what if one field is different? So, it could be, instead of u, it could be B, magnetic field or vorticity. Then one of them must be complex conjugate, other one is not. So, you have to have this, or I could have put a star here and not get rid of this. Okay, that is same. So, one of them must be complex conjugated. Okay. So, we will need these properties for when I go to describe fluid flows and energy and helicity and so on. So, is this idea clear? So, this is what is discussion on Fourier transforms. Okay, this is a crash course or crash module. Okay, so we stop. Thank you.